So my topic today indeed is twisted bilayer graphene. I know that some people there have an interest in this topic, so feel free to interrupt me at any stage. Most of what I'll talk about is contained in a bunch of recent preprints, which reflect the fact that I was drawn back into the subject by the experimental progress at MIT and elsewhere. So, twisted graphene is an example of a Moire superlattice. It's not the only example. These Moire superlattices are formed when you overlay two-dimensional crystals that are slightly different, either rotated by a small angle relative to each other, or with small lattice constants. And those small differences introduce a long length scale on which the coordination between the two layers slowly changes. And so when I talk about Moire materials, I will always have in mind two-dimensional crystals with the Moire pattern, as I described, but also that the host two-dimensional crystals are semiconductors or semi-metals. That is to say that the low energy states relevant for the properties that are of interest are all localized in a small region of momentum space. And when that condition is satisfied, it means that the low energy properties can be described by an effective model that has only the periodicity of the Moire pattern, giving you basically an artificial crystal with a large lattice constant that's tunable and proper electronic properties that are easily tunable by changing twist angles or applying gate voltages or other tuning knobs. So the first success in realizing a Moire superlattice was achieved with graphene, thanks to progress with tear and stack techniques for creating heterojunctions of these two-dimensional materials with controlled twist angles. And progress at Columbia and MIT, and also a lot of important work by my colleague at UT Austin, Emmanuel Tutuk, which eventually led to the controlled realization of bilayer graphene at a twist angle where correlations were known previously to be strong. And so my talk is about the properties that people have observed in those systems and trying to progress towards understanding them. As you'll see from my talk, twisted graphene is a little bit different from typical crystals in that, especially in that it's topological, its bands are topological in a very strong and unique way. But there are other examples of Moire superlattices, for example, one in which a lot of experimental progress has been made, and it's very important and exciting, I think, is transition metal dichalcogenide, homo or hetero bilayers. And basically those systems provide a realization of physics that's very close to what commonly occurs in strongly correlated materials. And so, for example, there's a recent paper from papers from Columbia and from Cornell experimental groups where they studied experimentally the metal insulator transition in a two-dimensional crystal simply by tuning the T over U ratio experimentally. One can hope there are many more to come. And I've listed there a couple that are potentially interesting. It really depends on progress with developing the tear and stack techniques and growing high quality bulk crystals and only if the mechanical properties are correct or are favorable can you make metastable Moire superlattices. So we'll see how it comes with other materials in the future. But my topic is graphene. So this is a band structure of a single graphene sheet. The relevant low energy states are the pi orbitals, odd under inversion in the graphene plane, blue on this energy versus momentum plot. You see it satisfies my criteria for a host for a Moire material in that its low energy states are in narrow regions of momentum space, actually near 2 points in momentum space that are related by time reversal, these inequivalent Brouin zone corner points. And there are two bands there are two bands that cross actually at these Brouin zone corner points. And the fact that there are two bands is related to the fact that the honeycomb lattice of graphene has two sublattices. And so that's that ingredient is the starting point for the interesting properties of magic angle or of twisted graphene systems. Many of those properties already appear in graphene two-dimensional electron gases. Whoops, just trying to move my gallery out of the way. And what I referring to here, graphene multilayer 2DEGs, by which I mean even in systems without a Moire pattern, graphene multilayers have interesting properties. You can simply understand the properties of graphene multilayers depend very much on how they're stacked, and this shows two common ways of stacking three-layer systems. If a carbon atom in one of the graphene sheets on one of the sublattices has a near neighbor directly above or below it in the layer stack, then the hybridization of those levels basically pushes them away from the Fermi level, and they're not really present at low energies. So the stacking in these multi-layers influences how many states are present, how many bands, how many states for a given momentum are present at low energies. And you can see this example. This is an ABA trilayer. So this ABA trilayer is closely related to twisted trilayer graphene. That will be important in my talk. In these so-called in ABC stacking, what happens is that the only low energy degrees of freedom are localized on the outside layers. And this is a generalization of what happens just with a bilayer, which I've illustrated on the right-hand side of this slide. And so this, what's shown on the right-hand slide is 2D momentum, kx, ky, and the wave function of the low energy states, actually the low energy state that's occupied at neutrality, the valence band state, as a function of wave vector, represented on a block sphere of being in the bottom layer like this, or being in the top layer. So the same type of representation applies for ABC trilayers. What this plot is showing you, the arrows represent the phase difference between the components on the two sublattices. And so on a block sphere, two-level block sphere, that phase difference is makes the state vector go around lines of constant latitude. And actually in AB bilayer, the wave functions are always half in one layer, half in another layer. But so you can see the topological properties of the bands. And actually, if you integrate over momentum space, you can see that these block states cover one hemisphere of the blocks of a block sphere twice, which means they have a Chern number of 1 and in bilayers. And as indicated both by these color code here, which is the sublattice or layer polarization of these states, they have a strong tendency to break symmetries, which opens up a gap in the spectrum and polarizes the band states either to one layer or another. And that opening up of a gap and the spontaneous layer polarization is, of course, necessary to get a non-zero Berry curvature for these states and to get the Chern number of these states equal to 1, let's say. And so this, I should have to emphasize that these bands here are projected to one of the two corners of the Brouin zone that I was pointing to before. So we use the word valley to identify which momentum, which Brouin zone corner particular momentum is close to. And so these are the bands projected to one of the two valleys. So valley projected bands tend to be topologically non-trivial, even without Moire superlattices. And indeed, this property is quite clear in old experiments on just graphene bilayers. What's illustrated on the left-hand side here schematically is that there are four each band has a multiplicity of 4. I'm going to refer to this as flavors, 4 flavors. The states can be near either Brouin zone corner in either valley, or of course they can be in one of 2 spin states. And in the ground state, for each flavor, the layer symmetry is broken, but it can be broken in many different ways. And among these various possibilities, if the sense of layer polarization is the same for 2 different flavors, then by time reversal, they give opposite contribution to the Hall conductivity. That's represented by these corners of these lines. The ground state is actually a spin density wave, which is actually represented by this cartoon. But the big energy scales are associated with layer polarization within a valley. And the small energy scales determine the relative sense of layer polarizations in different valleys. And the state B here, in which all 4 flavors make the same contribution to the Hall conductivity, is not very far away in energy. And so that the way that appears experimentally is if you look for energy gaps in this system, and this is an old experiments from Amir Yacobi's group, it shows that there's an energy gap at a density that depends on magnetic field. And this is as you know, this is an indication of a quantum Hall effect. And the fact that it persists essentially down to 0 field means that this there's a nearby state, not quite the ground state, it turns out, that has a quantum anomalous Hall effect. And of course, So this is what, these appear all over the place in twisted graphene as well, this kind of effect, where there are states with different Chern numbers that are nearby in energy, and higher Chern number states can be stabilized by applying magnetic fields. So that kind of physics already appears in graphene multilayer 2DEGs, although it only appears if you take away the surrounding dielectric material. So these observations are made in suspended graphene bilayers. And by making the bands narrower, as I'll discuss next, the correlations become strong enough that these quantum anomalous Hall states appear even in more controllable samples, which are encapsulated by hexagonal boron nitride dielectric. Very recently, thanks to partly to advances in sample quality over the years, there's a recent preprint just this month from Andrea Young's group showing this kind of physics, not in a suspended sample, but an encapsulated sample in ABC trilayers. Turns out the trilayer bands are a little bit flatter than bilayers, and evidently that tips things over the edge. And you can see this kind of behavior, spontaneous layer polarization in trilayers. Okay, so now I'm going to, with that prelude, switch to talk about mostly about twisted bilayer graphene, and the flavor, dependent topological properties of the bands are going to be very important. I'm going to say that there are two things that we know mostly from experiment, although they're very natural, or from a theory point of view, also is that there's an additional ingredient in I shouldn't say this occurs even in ABC trilayers, but that is much stronger in the Moire superlattice materials, and that is that that the populations of these different spin valley flavors are unequal in many cases. That's one thing I'm saying that we know about magic angle twisted bilayer graphene. And we also know, I believe, that the superconductivity is spin triplet superconductivity. There are lots of things we don't know, but I think we're making progress, and I'll talk about that towards the end of my talk. Okay, so this is bilayer graphene. This is actually a picture of the electronic structure familiar to many of you of AB Bernal stacked bilayer graphene. In these graphene multilayers, the different layers interact with each other mainly via electrons tunneling back and forth between the two layers. And this is the bands that you see here at the Brouin zone corner correspond to the cartoon I showed you earlier. There are two bands that are pushed away from the Fermi level by a few tenths of a volt, which most of the time is a large energy. And there are two bands that actually cross quadratically at the Fermi level in AB Bernal bilayer graphene. And so the energy scale associated with interlayer tunneling is the amount by which these are these two higher energy bands are pushed away from each other, maybe 4/10 of a volt or something like that, and that will be a high energy for the rest of my talk. And so what is the physics of twisted bilayer graphene? The layers communicate with each other because of tunneling from layer to layer. And if you make a Moire, and that the way they communicate with each other is dependent on how the two layers are coordinated. The position of the honeycomb in one layer relative to the position of the honeycomb in the layer below. And so the model that describes twisted bilayer graphene is a model with two graphene sheets linearly crossing bands and tunneling between the layers that's position dependent, that varies slowly in space on the scale of the Moire pattern. And for example, at some points where the stacking is AB or BA, the electronic structure is just the one I showed you a moment ago. But this plot is actually a plot of one of 4 interlayer tunneling amplitudes, because there are 2 sublattices in each layer, 2 bands. The tunneling between the layers is sublattice dependent. This is just showing one of those amplitudes, which is a complex number plotted as a magnitude and a phase by the length and direction of these arrows. And the main thing to notice here is that it has the periodicity of the Moire pattern, that it when you have local AB stacking, for example, all of these tunneling amplitudes are reduced to the known values at those high symmetry stacking points, and more or less just interpolate smoothly between them. And so in this way, you can get a simple one parameter actually model for the electronic structure. And if you specify, essentially 0 parameter model. And if you specify the twist angle, and this is that model. So these are sublattice dependent interlayer tunneling amplitudes dependent on local coordination, position through local coordination, varying slowly in space. So this is a, smooth Fourier space expansion of that tunneling amplitude. And magically, and I won't be talking about this today, it turns out that the interference, if you like, between this position-dependent tunneling between the layers and the direct dispersion within the layers at a set of magic angles, the largest of which is around 1 degree, the bands that are closest to the Fermi surface become extremely flat, and correlations therefore will be extremely strong. So I should point out, in these flat bands, this is energy vertically versus momentum. The bands aren't flat if you go either side of this magic angle, but there are 8 of these bands. You can see 2 of them here, a conduction band and a valence band. Each of these bands has a 4-fold flavor degeneracy. So when you are between -4 electrons, and this relative to a neutral system, when you remove up to 4 electrons per Moire period and add up to 4 electrons per Moire period, then the Fermi level lies in these flat bands. And so that's a range of density of about 8 times 10 to the 12, 10 to the 13 per square centimeter, which is just comfortably and kindly matches the range of density that is convenient, the number of electrons that you can remove or add from a two-dimensional layer using electrical gates. So you can study the physics as you take these flat bands and completely fill them, completely empty them, and go a little bit beyond that. So all of the interesting region is accessible. Now you'll notice this is from the original paper we wrote on this magic angle. And you'll notice that I have these flat bands here, but the other bands, which I call the remote bands, are not very far away in energy. So it turns out, again, kindly, that subsequent work which derived improved models of twisted bilayer graphene, improved by accounting for the corrugations of the bilayers, which follows the Moire pattern, and also strains that accompany the twists. In other words, once you twist the two layers, they don't remain completely rigid, nearly so, but not exactly. And those changes actually, turns out, remove these flat bands from the remote bands further away from the flat bands. So you have essentially spectrally isolated bands in which the electron velocities are very small, perhaps 1,000 or so times smaller in practice than they are in a single graphene sheet. So this slowing down brings strong correlations. And now that we can do experiments, thanks to the experimental progress I mentioned at the beginning, we actually know the properties of these twisted bilayer graphene, and we're trying to puzzle out what they are and why. Okay, so this is one typical type of experimental data you get on bilayer graphene. I think this data I'm showing is actually from, I have to move my gallery to see the bottom. Yeah, so this is, this particular data is from Andrea Young's group, but similar data has been obtained by all of the other groups active in this area. First place by Pablo Herrero's group, also Dmitry Yefetov, Corey Dean, and so on. And so, this is a color scale plot of resistance versus magnetic field. I'm going to talk a lot about in-plane magnetic fields in a moment, but let's concentrate here on perpendicular magnetic fields. This is removing electrons from neutral twisted bilayer graphene. On the left-hand side, you've removed 4. And what the data shows you is you see Shubnikov-de-Haas oscillations. As you start to remove carriers, that means you have a Fermi surface. And at filling factor -2, you have a insulating state that doesn't appear in the single particle theory because the 4 bands at this point are half empty. But then when you remove more carriers, you have Fermi surfaces again. And down here in dark blue, that's where the superconductivity is. And I'm going to be talking about important lesson on how the superconductivity depends on in-plane magnetic fields. Okay, so this slide is trying to highlight one of the extra pieces of physics that you get from the Moire superlattice. So I'm plotting here a blue density of states. It's supposed to be cartoon for density of states. And so blue is valence band, and the white area is conduction band. So there are 2 bands for each of 4 flavors. And the physics I showed you, the quantum anomalous Hall effect, for example, in suspended bilayer graphene electron gas that I talked about at the beginning, that happens always when the system is neutral. And you can open up a gap at neutrality by breaking some lattice symmetry. And it always makes the bands topological. So the thing that's different when I have the Moire superlattices is that the valence band states that are occupied in neutrality, at neutrality, and the conduction band states that are empty at neutrality are, their bandwidths are finite. The the full infinite negative energy C of the bilayer problem, a little piece of it is separated off. That's the flat bands, and that's a narrow band. And because of that, you can form broken symmetry states in which you occupy some of the flat bands and leave the other ones empty. So I'm going to say that we know from experiment that these states are common in twisted bilayer graphene. And the first case evidence for that probably is the fact that twisted bilayer graphene has a quantum anomalous Hall effect when there are insulating states at odd integer filling factors. And that's what we expect because, each band should have a non-zero Chern number and therefore contribute, one quantized unit to the quantum Hall effect. And if the number of bands is odd, they can't cancel each other. So the strongest observations are in twisted bilayer graphene. Actually, I haven't emphasized, but alignment with hexagonal boron nitride plays a part in this story. But you see a very experimentally a pretty accurate couple of percent quantum anomalous Hall effect in the system, which is understood as demonstration that the valence, let's say that the conduction band has been emptied in this case for only one of four flavors, and that's the insulating state at filling factor -3. So that's one evidence that that these spontaneous flavor polarization effects occur. And here's another one. This is actually what I'm showing you on top here is data from Andre Young. The cartoons on top are trying to describe what's going on, but this is actually starting at neutrality and going to removing electrons, introducing holes. And it's a measurement of the weak field Hall effect, which is a measurement of the area of the Fermi surface, and whether it's an electron-like Fermi surface or a hole-like Fermi surface. So this experiment says that I start from neutral graphene, start removing electrons. I have a hole-like Fermi surface that's getting bigger and bigger, and suddenly I have no carriers present. This is actually occurs close to the insulating state at -2. And when I go below -2, I start over making a Fermi surface. And the interpretation of that is that, that only 2 of the 4 flavors are partially occupied, and you're seeing the Fermi surface of those flavors as they become less than half full. Interestingly, I won't dwell on this, but very similar things are seen in cuprates, these kinds of jumps in Hall conductivity. And so the takeaway is magic angle twisted bilayer graphene has these states with different populations for the different flavors, which should be the same by symmetry. It's a Q equals 0 type broken symmetry. There may be a couple of cases in which broken translational symmetry states are also seen, but this is some kind of generalized ferromagnetism like we get in commonly in metals, where this population of majority and minority spins spontaneously differs, and simplest description of that is sort of a mean field description in which magnetism is driven in metals by exchange interactions among electrons that share the same spin. And it's no doubt that at the zeroth order level, it's qualitatively the same thing that's driving these states. In twisted bilayer graphene, that it's really exchange interactions that favor occupying more states that have the same flavor. And but there are a couple of interesting differences, which I'll just quickly mention. I see time is running on. How much time have I used, Jennifer, or G?
Half an hour.
Yeah, 4 minutes, but you can.
Okay.
30 minutes. 30 minutes.
Okay.
Sorry, 30 minutes.
Okay. So I should
but
wrap
you
up
can
in
run
20
late.
minutes.
It's fine. Actually, it's totally fine if you run late.
Okay.
Yeah.
Okay. So what I'm saying here, and so this is, if you know some density of states, you could write down a similar mean field Stoner-like model in this case. And the main point I want to make here is that there are 4 flavors, not 2 flavors. So with 2 flavors at a fixed total density, then there is only one order parameter, if you like, neglecting the dependence on directions of magnetizations. And here there are 3, because there are 4 flavors, and the constraint is that the electron density has to be kept fixed. So there are 3 order parameters which you can choose to be an overall spin polarization, an overall valley polarization, and something else which measures the difference, if you like, between the spin polarizations of the 2 valleys. And with these 4 parameters, you can see that this cubic term, which is not allowed by time reversal in the ordinary magnetism case, is allowed. And so that already, that means that these transitions will have a tendency to be first order, and in which the valley, the polarization emerges. And so it turns out that actually even in ordinary metals, if you tune the parameters so that you go from a non-magnetic state to a ferromagnetic state, that's of course very hard to do in real materials, because it depends whether or not you have magnetism. It's a strong coupling instability, depends on a balance between 2 large energy scales, exchange energies and band energies. And so there are only a few materials that they're close enough to being in balance that you can tune through with some nod, typically pressure. But when you can do it, so people have been interested in this as a quantum phase transition, and Andy contributed a lot to this over the years. And what people take away message from all this work, described, for example, in this review article, is that these transitions are always first order. As you approach in pressure taking pressure away will make the bands flatter, and and tilt you towards a magnetic state. And so it turns out that magnetization jumps up. And in particular, that if there's a phenomena people often refer to as metamagnetism, that if you're close to this boundary and you apply a magnetic field, you will suddenly jump up to a large magnetization discontinuously. And this comes actually, let me skip this. The origin of that behavior is actually non-analytic correct dependence of the energy on the spin polarization order parameter that just comes from intricacies of the phase space for electron-electron scattering and how it depends on filling factor. And the same kinds of things occur in this system if you have, should be expected, if indeed this region between what I'm showing here, region between neutrality and filling factor near -2, your tuning, as you're near somewhere near -2, that's where you first have at zero field spontaneous flavor polarization, and which includes spin polarization, of course. And as you approach that, it seems like in a magnetic field, you have a very similar wing on the phase diagram in which there's kind of a metamagnetic state. So this all hangs together. Let me skip this. And so to draw a line under that, one part of the physics of magic angle twisted bilayer graphene is a generalized form of ferromagnetism. And I did not emphasize it, but I should have emphasized that the flavor polarization, spontaneous difference in the occupations of different flavors occurs not only in insulating states, but also in metallic states. So now I'm going to turn to a different property, that perhaps the most interesting property and surprising property of this system is that it's a superconductor. And it's going to turn out these two things are related to each other in a way I'll explain. And I'm showing you now some data from a very recent preprint from the Pablo Herrero group at MIT. What you see in this plot is just IV dissipationless transport up to a critical current. You can see that although the critical current gets smaller, the superconductivity, dissipationless transport persists up to magnetic fields that are in the neighborhood of 10 Tesla. And it turns out if you plug in the numbers, that the Zeeman splitting at 10 Tesla is substantially larger than the superconducting gap that you would infer from the critical temperature of superconductivity. I pointed to at the beginning, superconductivity occurs at filling factor a -2.4. So it's, and I'll concentrate on the hole side, but similarly on the electron side. So it seems that the superconductivity is occurring as an instability of a state that's already flavor polarized spontaneously. And this exceeding the Pauli limit by a large amount occurs in trilayers, but doesn't occur in bilayers. At least it's not so obvious in bilayers. And I'm going to say that there's an important lesson in that. Okay, so first thing I want to say is that these tri-layers are actually middle layer twist tri-layers. And, you know, as emphasized first, I think, by Islam Khalaf at Harvard, these and collaborators, these tri-layers and bilayers are nearly identical in the following sense. So they have the same symmetry as the ABA 2-DEG tri-layers that I talked about at the beginning, because the hopping from the bottom to the middle layer, which has been twisted, is exactly the same as the hopping from the middle layer to the top layer. And what that symmetry does is it makes in the single particle level, you know, the parity under mirror symmetry in the middle layer is a good quantum number. And you can classify the states as even combinations, or, you know, states that are even under mirror symmetry. That means either they're in the middle layer or they're a symmetric combination of the outside layers, or as odd parity states, which have to be an antisymmetric combination of the outside layers. And if you look at the electronic structure, so this is middle layer twist, this is just an example. Somewhere, turns out that the magic twist angle goes up a little bit. So this is close to the magic twist angle. And the odd parity bands look like an isolated graphene layer. And so they're just hanging around, they don't do much. But if you just look at the even parity states, they're essentially the same as in twisted bilayer graphene. So I would argue that it's almost certain that the mechanism of superconductivity in bilayers and trilayers is the same. And so that assumption will be underlie the conclusions that I reach below. And so
a question about the band structure, actually. Sorry if you said this, I got disconnected for a moment, but so here, flat band, there's a Dirac cone which is crossing through the flat bands. So the flat bands are not isolated in energy from the conduction in bands. Is that important at all? Because, you know, in the bilayer case, you kind of emphasize that.
Yeah, so, you know, the density of states in this highly dispersive odd parity band is so low, I think it just doesn't matter for the superconductivity.
Okay. So the point is that the flat band, we should really only care about the flat band, and whether it's isolated from other bands doesn't matter, especially because it's Dirac cone, which has negligible density of states at that point. Yeah.
So, you know, over this width of gating that we've been talking about, of a density of a few times, you know, 10 to the 12 or something, Fermi level gets pinned in these flat bands. And so they're just, you know, there are some of these odd parity bands that make a negligible contribution to the density states. I don't think they play any role in superconductivity, but that's definitely, you know, at one time I was thinking that these dispersive bands would help to make the superfluid density larger. So they could potentially play some role, but I think they play a very small role. Okay. So, but anyway, the claim is they play no role, but that's up for discussion. Okay. So, so the observation is that an in-plane magnetic field, which you know, doesn't produce any vortices or anything like that. Very often we think all an in-plane magnetic field does is that it produces Zeeman coupling. But in these systems, there's also an orbital effect of an in-plane magnetic field. And what I'm going to say now is that that orbital effect is very different in bilayers and trilayers. And so here is on just moving the gallery again. Here is on the top this, interlayer tunneling amplitude I talked about before. That's responsible for the Moire pattern, basically, in the or how it impacts electronic properties. And its Fourier representation is given here. And so you can see that in this model, when you tunnel from one layer to another, you get a momentum boost because of these the spatial modulation of the Moire pattern. There are 3 different momentum boosts you can get. And so these 3 QJs, I should have a plot here, but there are 3, wave vectors that have a size that's reciprocal to the Moire pattern and that are 120 degrees to each other. And the point I want to emphasize is that if you look at the 2 different valleys, these Qs change sign. And that really just follows from time reversal symmetry. And time reversal symmetry, of course, is very important in superconductivity because it guarantees the degeneracy normally of states that have opposite momentum. So the interlayer tunneling in the absence of a magnetic field, is a time reversal invariant contribution to the Hamiltonian. And so what happens when you add a magnetic field? So this is something we're very used to in these 2D systems, that if you put an in-plane magnetic field, what it does is it shifts the momentum space of one layer relative to the other. That shift in the momentum space just corresponds, keeps track of the Aronoff-Bohm phases that you pick up if you go through, around a loop that tunnels between the 2 layers at one point and tunnels back at some other point. And so you get a momentum boost that is proportional to the layer separation, proportional to the in-plane field, related to the magnetic flux quantum. And the important point is that this momentum boost, which just adds to these momentum boosts up here, is layer independent, is valley independent. And so it's not opposite sign in the 2 valleys. And that means that the bands are no longer time reversal invariant. And so let's look at what that does to the band. So this is a model of the band structure of twisted bilayer graphene, comparing twisted bilayer graphene, twisted trilayer graphene. What I've overlaid there in blue and red, if you concentrate just on the left-hand side first, is for some model of the band structure, I've overlaid, some constant energy surfaces, Fermi surface, that's some band filling, and what I've plotted is the energy in one valley, or constant energy surface in K space in one valley, and the constant energy surface in the other valley, but with momentum reversed. And you can see that these 2 constant energy surfaces are different. And that means that it's no longer true in magic angle twisted bilayer graphene that the energy in one valley is the same as the energy in the other valley at the opposite momentum. So this comes from these momentum boosts. But in trilayer graphene, if the other layer, if one of the 2 effective layers is the middle layer, and the other layer is a linear combination of 2 layers that are whose vertical separations are opposite. So the average positions, if you like, of the two layers is the same. And it turns out you can, examine that more formally, and that in fact, an in-plane magnetic field, basically because of the mirror symmetry that I was talking about before, an in-plane magnetic field for twisted trilayer graphene doesn't interfere with the nesting between K and minus K Fermi surfaces. And there's no pair breaking effect in that way. So here's a specific calculation, microscopic calculation, solving the mean field equations in the presence, assuming that all of the states have the same spin orientation. So, so there's no Zeeman energy involved in this, at least for, here I'm talking about the solid blue, and I'll comment in a moment on the solid red lines. But the solid blue line shows that, that basically in-plane magnetic field does not destroy superconductivity in twisted trilayer graphene. The inset shows the corresponding calculation for bilayer graphene. It does. The orbital effect destroys superconductivity even without Zeeman. The two effects actually work in have quantitatively similar pair breaking effects. The red line, dashed line here, shows you what would happen. What would the, if I imagine that the pairing electrons had opposite spins, and you can see that you would not be able to sustain such high fields here. Whoops, I should be pointing to the blue line here. The red lines are what happens when you add a displacement field. And the displacement field destroys, as that's electric field perpendicular to the trilayer structure, destroys this parity symmetry. And there, once you do that, then an in-plane field will have a pair breaking effect and destroy superconductivity. And so the conclusion I want to draw is that the fact that superconductivity survives out to extremely large fields in twisted trilayer graphene suggests that the flavor polarization is such, that you have basically a ferromagnetic state, that superconductivity emerges as an instability of a two-dimensional ferromagnet. And this is consistent with the data not only in the trilayer graphene, but also in the bilayer. We don't see this effect in bilayers simply because in bilayers there's a strong pair breaking effect that's purely orbital. Okay, so I think I'd better go on. And can I take 5 minutes?
Yeah, of course. May I ask one question?
Sure.
Yes, earlier you told that without displacement field, the trilayer band structure is essentially can be decomposed into mirror even and mirror odd sector. And in the mirror even sector, the band structure is basically similar to the bilayer graphene, right?
Yes.
But then why you apply an in-plane magnetic field, you see a difference between bilayer and the trilayer? I mean, the band is the same. What's happening?
Yeah, the two systems respond very differently to an in-plane magnetic field. And the easiest way to understand it is, when you have a bilayer, there is a large orbital effect of an in-plane field. When you have a trilayer, Yep. Okay. Step back. There's a large orbital effect because the two layers are displaced vertical. And so there's, AB flux that goes between the layers. That's what the orbital effect is. In the case of the tri-layer, the three layer, the two layers, the effective bilayer is the middle layer and the two outside layers together. And the average position of the two outside layers is the same position as the middle layer. Okay, so there's effectively the layer separation between the two layers, and the tri-layer case is 0. And you could say that more formally. It's really true that when you add via this mechanism an in-plane field in the tri-layer case, there's no effect on superconductivity.
Yeah, that's very interesting. So is this work published on arXiv?
It's on the arXiv, yeah.
I see. So I will read it afterwards. So
Okay.
I also have related questions to the reentrant superconductivity. So I read your paper like 30 years ago. You discussed the reentrant superconductivity in the if you have out of plane magnetic field. That's basically because of the Landau orbital quantization effect.
Yeah.
Do you see any aspect that it's clear that these two systems is very different? One is in plane, one is out plane. Do you see any common aspect of this?
Yeah, so they're quite different, and so they're not related at all. Let me talk a little bit about the reentrant superconductivity in a perpendicular field in 2D superconductors, with small Fermi surfaces and therefore, low Landau indexes near the Fermi level. Actually, I in the summer of 1989 or thereabouts, I visited Argonne National Labs, and my friend Mike Norman for a couple of weeks and or a little while, and so we were. I was working on quantum Hall effect in those days, and he was working on superconductivity. So we wanted to look at something in, so we settled on something in between, which is, what happens to superconductivity in a perpendicular magnetic field when you look at it in a representation of quantized Landau levels. And what happens at the level of mean field theory is there's definitely reentrant superconductivity. And, what the origin of this is simply, the pair breaking effect of a magnetic field is, that the wave functions are no longer time reversal invariant. And, but this gets trumped if you have, in mean field theory, Landau levels give you a big peak in the density of states. And so the big question about that is, we've always been wanting to find an example where this was realized in nature. And there are some systems where you have big Fermi surfaces, but you also have a little piece of Fermi surface. And there's and Landau quantization is important on the little piece of Fermi surface in some multi-band superconductor, but we want an example where it was really the what was carrying the superconducting order. So if mean field theory is right, and that's a big question mark in a strong quantizing magnetic field about whether it gives a correct description of superconductivity, then this magic angle system is the perfect system to look for this. And so I will be very happy boy if indeed reentrant superconductivity is seen in a perpendicular field. But it's more speculative, I would say.
Yeah,
okay.
Thanks.
Yeah. Okay, so I sent, I gave too long an answer. So let me just end quickly. And, you know, I referred to before about the superfluid density of these superconductors, which is does have a dependence on in-plane magnetic field. And we would like to understand it and relate it to experiments which also, you know, I think see this dependence on in-plane field through studies of the costless thallus transition. I'm referring to the recent paper from the MIT group. But there's a problem. And here's the problem. We don't really, with any confidence, know the band structure of twisted trilayer graphene. And let me explain briefly what the problem is. So in this slide, in the dashed lines, I'm showing you the band structure at neutrality in twisted trilayer graphene. And so this is what I've been talking about up till now with this tunneling model and so on. And this is actually a version of that band structure where we try to tweak things like include strain effects so you don't see any of these remote bands, and include non-locality in the interlayer tunneling, which causes particle hole symmetry breaking. So we get these bands like this. The top of the conduction band, bottom of the valence band is at gamma in all these calculations. And exactly how far the energies go away at gamma is sensitive. But the band structure in these systems has to be strongly dependent on band filling factor just from mean field effects. And it's related to the fact that the wave functions of the different states in the Moire superlattice are actually, the states near gamma have wave functions concentrated in one part of the Moire-Brouin zone, and states near kappa kappa prime here in the Moire-Brouin zone, their wave functions are concentrated somewhere else. And so depending which bands you're emptying, the band structure changes, and you can easily calculate what the band structure looks like when you completely remove all the carriers, because then you again have a single Slater determinant state. And what happens is, for example, this is the band structure with the valence band completely empty in blue. And so are the states at gamma the lowest energy states, are they at gamma, or are they at this point halfway between kappa and kappa prime? Has a big effect on many electronic properties. And if you try to build any kind of concrete model, and it depends very delicately on gate screening, on exactly what you think the band structure looks like at neutrality. And so that's a challenge. I think it's a solvable challenge, by continually trying to compare with experiment, but that's been an obstacle. And another, problem is that if we want to describe these flavor symmetry breaking transitions microscopically, so far, we don't have a theory that does this successfully. Mean field theory, or Hartree-Fock mean field theory in the metallic states strongly overestimates the tendency towards flavor symmetry breaking. This is just showing, energy in this, some 2D cut of this three-dimensional order parameter space I mentioned before. And, so I think the poster child for this is there is an insulating broken symmetry state at filling factor -1. Experimentally, it's not seen. But if you add a fairly modest magnetic field, it appears. So it seems like the system at filling factor -1, doesn't have any broken symmetries, but it's not far away in energy from states that do. And so question is, can we do a microscopic theory that will capture that state, properly, predict properly whether or not we have flavor symmetry breaking? And, the last thing we don't understand, of course, is the mechanism for superconductivity. And one of the mechanisms is phonons. Could potentially be just the usual combination of phonons and competing with repulsive Coulomb interactions. But there are hints in a variety of properties I won't go through that that it's not phonons. And independent of estimating electron-phonon coupling strengths from phonon limited resistivities and how that compares with actually measured resistivities, there is another property from experiment illustrated here, and this is also discussed in a recent preprint, but we don't know exactly the band structure, as I said. Often we don't know, for example, where are the Van Hove singularities and how far away are we from them? But you can measure, one way of measuring the typical velocity of electrons at the Fermi level is by combining, at least within mean field theory, the critical temperature and the critical magnetic field, a perpendicular critical magnetic field. And normally in any kind of theory where the mechanism for pairing has nothing to do really, the glue is not self-created by the electrons in the band, it's something external, then you get a TC maximum where the velocities are smallest, where the density of states is biggest. And this is just showing, some calculation with a model of the band structure that might not be right, that, you always see that property if you just put in by hand some phenomenological pairing interaction, but it's not seen in experiment. There's actually this anti-correlation between the effective velocity and where TC is maximized, which is where the density of states is maximized here, is not seen in experiment. So it seems like, this magic filling factor region around -2.4 has a self-generated pairing that's only present around those filling factors. And we don't really know what it is yet. Many people are working on this from different points of view. We've actually been looking at generalizations of, paramagnon mediated type superconductivity being close to instabilities, creates, repeated scattering in different particle hole channels, can give you effective interactions. And this is known, for example, or usually accepted as the explanation for why nearly ferromagnetic metals like palladium are not, or platinum are not superconductors. And in the case of twisted bilayer graphene, there are various kinds of particle hole channel instabilities that can occur, some of which support this valley singlet superconductivity I was talking about, some of which oppose, and maybe there's an explanation there. So let me sorry for going over slightly, whoops, more than slightly. Let me just leave it there. Thank you so much for your patience.
Thanks, Allan. Thanks for the very interesting talk. Are there questions? Maybe I can start with a question, actually. coming back to the superconductivity in trilayer graphene, we were talking about the stacking, which has the mirror symmetry, but there's other ways to stack it which don't have the mirror symmetry. So is the superconductivity not observed in the twisted trilayer graphene, which is not mirror symmetric, or is it not as robust to the in-plane field? That would be a test, right?
Yes, and I don't know, actually, maybe somebody else on the call knows. I don't know whether that's established experimentally. It seems like superconductivity is associated with magic angle flat bands, and the magic angle flat bands only occur for this middle layer twist trilayer.
Okay, I see.
So in the other case, we don't have flat bands. So it would be definitely, interesting if we saw superconductivity in top layer twist trilayer, for example, because that would tell us that flat bands, these are not necessary for superconductivity. But I think the experimental evidence is that they are.
I see. And maybe another way to test this would be if you had HBN on one side, would that also break the mirror symmetry and maybe change the robustness?
That's interesting. If you aligned HBN on one side and not on the other side, that would be interesting. They, experimentally, they break this symmetry with a displacement field. And I'm not sure if I have the experimental data here, but definitely large enough displacement field will mean that you don't exceed the Pauli limit by so much. But one thing that happens in our calculations, like this blue line here, when we have the mirror symmetry, there's no hint in our model up to arbitrary field that the superconductivity goes away. That's not what the experimental finding is. They do find eventually they destroy the superconductivity. And our interpretation of that finding is that there are, random electric potentials in the system that effectively make a random variation of displacement field across the system. And, in support of, so we think that, it's that random displacement field that's actually destroying the symmetry locally and making the superconductivity go away. And I think there's some evidence of that and consistency in that, at least looking at the experiments, it seems like better devices have even higher in-plane critical fields.
I see. Thanks. Are there any other questions from the audience? Shiwei?
Yeah, I have a question. Hi, Allan.
Hi, how are you?
Good, a very illuminating talk. So I have a very naive question because I have no intuition on the system. But if I take the related to superconductivity, if I think of the system as basically a very dilute, low density electron gas with fancy phase hopping and with the in-plane magnetic field changing the hopping in some in a particular way, how wrong is that model to think about superconductivity?
I think let me answer the question in a different way. I think you could have a lattice model which has the same effect, has the same basic thing going on.
Right. But you
if
want the
made
long
it-
range interaction in there on the lattice model.
What do you mean by long range interaction?
Well, relative to the particle spacing, is it enough to consider sort of a short range near neighbor type of interaction on a lattice model? I mean, the lattice could be very.
I think if you made a 3-layer lattice model
Mhm.
with mirror symmetry,
Mhm.
and yeah, I think I think you can at least cook up a model which has exactly the property that twisted trilayer graphene has, that the mirror symmetry survives an in-plane magnetic
Right.
field.
So in that model, is it important to have what mimics a Coulomb interaction, or is a shorter range interaction sufficient, do you think?
Yeah, I think I think there are interesting questions you could look at with a short range interaction model.
I see.
So that's a great idea, actually. Maybe
So then,
attractive view Hubbard model that.
right. So then, should I think about the pair when superconductivity happens as more a real space, a short range pair of triplet, or should I think about it as more like the BCS limit of momentum space pair?
Yeah, well, these systems we know from HC2 and TC that the coherence length is a couple of lattice constants, right? So compared to typical, yeah, so it's pretty local. And that's connected, of course, to the fact that the ratio of the gap to the bandwidth is not an extremely small number.
Interesting. Thank you. I'll read.
Okay.
I'll read up more.
Okay. Yeah. Anybody wants to follow up with any questions, they can send me an email. Be very interested to interact.
I just came up with a related questions. Maybe you must also already know that in the Cairo model of twisted barrier graphene, at magic angles, the band is exactly flat. And if you add out of plane magnetic fields, they're with certain, if you have integer flux in a unit cell, the band is also flat. There is some reentrant flat band. So I just wonder whether the problem of Cairo twisted barrier graphene with in-plane magnetic field has been studied, whether there's some nice properties of the wave function in these models and giving some insights about superconductivity.
Yeah, so I'm not aware, but that's definitely a great idea to think about that. I'm pretty sure that's not been looked at.
I see.
And so as I indicated, I do think that some details of the band structure that are not captured by the chiral model are important for detailed features of the band structure in these systems, but it might well be that that model gives you a handle on some of the interaction effects that's correct and attractive.
Yeah.
Hi, this is Zari, and I have a very narrow question. So, like in the twisted barrier graphene, when we build the Moire brilliant zone, we will put the Moire key point to be the same position at the monolayer key point. And when I look at your previous paper on the heterostructure of TMD materials, we put the Moire gamma point at the key point of the monolayer TMD materials. So I wonder, is this like position determination important, or it's just a momentum shift?
I'm not sure I got the question entirely, but especially in the graphene multilayers, there are lots of momentum shifts you can do with different gauge choices that give you models that are look superficially different, but they're actually the same. So in the case of the TMDs, we're just in all of these cases, really, these models you can think of as semiconductor physics envelope function models. And in the TMD case, the natural thing you always do is measure momentum from the reference momentum, which is at the Brouin zone corner. So that's kind of what we always do, but because the graphene layers, you have two active layers that are actually twisted relative to each other, then the momenta at the Brouin zone corner is different in these two different layers, and that's where you can make different choices in how you represent the model.
So it's just a convention, like it's just a momentum
Just a convention.
shift.
Yeah.
Thank you.
Yeah. Okay.
So I have another question about the superconductivity, which is you're kind of proposing I guess a mean field term, but I was really wondering, does it give you any insight into the pairing mechanism? I mean, you kind of touched on this a little bit at the end, or not at all?
Yeah, so one thing I should have emphasized and didn't is that the bands within a valley are not invariant under k go to minus k, very strongly so, in fact. And so that means that just for this band structure reason, it seems overwhelmingly likely that the pairing occurs between electrons that are in opposite valleys.
Mm-hmm.
So what was the question again, Jen?
So I was really wondering if there's any insight into the mechanism, like driven or something like that.
Yeah, so it doesn't provide too much guidance on its own.
Okay.
Yeah, so some way you have to escape Coulomb interactions. Either because the Coulomb interactions are strongly screened by the flat bands in a dynamic way which is favorable, or somehow you find a channel that doesn't compete with the Coulomb interactions. That would have to be some sort of pairing that's non-local in space. Yeah, that's where I am right now. We think about this question a lot, but I don't really I don't have an answer I would insist that anybody else believes.
Yeah. Okay, and I have one last question, but it's just a more general question. In the models for twisted bilayer graphene, the interlayer tunneling seems to be the very important thing. But in the models for twisted TMD materials, the potential of one layer on the other seems to be a very important thing. So in general, if I was going to explore different material combinations, how do I know whether interlayer tunneling or interlayer potential or both is the important term to include?
Yeah, I think you have to do a microscopic calculation.
Okay, there's no trick to knowing this.
No, and in the TMDs, I think actually both effects are important.
Okay.
I think that in the TMD hetero bilayer, the tops of the valence bands in the two materials are at different energies, and you're only interested in one, but there is a level repulsion effect between the two layers, which is at least half of the Moire effective potential. So in the TMD heterobilayers, it's not really that the interlayer tunneling plays no role. It's just that it's far enough away in energy. You don't have both degrees of freedom present at once. That's why TMD homobilayers might be an extremely rich system going forward, where you imagine you have the capacity to, with gates, change the energy separation between states in one layer and the other, and therefore change whether degrees of freedom in both layers are active on the energy range of interest.